So in this section, we will continue the cellulosic materials and we will focus on corrugated board. So we will see the structure and a little bit on the box design, as we saw for the previous case, and some specifications for the corrugated board. In this case, we have a structure that is not as it was in the case of the board. We have a single or a double structure. We may also have triple structures and more, but the most common for boxes are the single and the double. And as we see, we have at least 3 elements. We have 2 liners and 1 fluting or corrugated layer in the between. And we have also a glue that is applied on top of the waves in order to fix the structure. And the liners and the flutings, they are made out of different types of papers typically, because they have different roles on this structure. The liners are responsible for the rigidity of the structure, for the bursting strength, for the tearing strength, and also for the printing. And typically is made in very resistant papers like kraft. It can be what is called white top. White top kraft is a B-layer paper where we have a kraft and a white paper layer on the top. That's why we call it white top. It can also be what is called in the industry as the test liner, that has an important percentage of recycled fiber. Then the fluting, concerning the grammars characteristics, the range typically is 130, 430 grams per square meter. So strong papers. For the fluting is responsible for resistance to flat crash or flat compression, for shock, and for compression of the box. So we want some slightly different characteristics, and typically is used semi-chemical version pulps and more recycled fibers. So the glue is applied, is a glue based in amide, that in English we should say starch. Okay, so this is something that I need to correct here also. Is starch-based glue, and there are specific formulations when the box is going to be used in high humidity environments, so to make it strong. And we can have resins like urea, formaldehyde, to better resistance. The glue is responsible for the stability of the whole structure. And so this is for the single. For the double is the same, and we have let's say a repetition of the structure, although we may have different characteristics, and I will explain. We have different fluting characteristics. So, and these are designated by letters. A, B, C, E, F, G, N. There are a few, and the most relevant. I don't know if you know why or why corrugated board was invented. It was invented to as a means to hold the hats of the Queen of England, to make it good resistance during the trips, so that the hats were not smashed. And that was done by a single structure without one layer. So if I take this layer out, so if I have just one liner and a flute, this becomes a flexible material that can be rolled up, and sometimes is used to hold bottles also. So this was the first, in fact, that was the first structure invented, so for the Queen hats. Later they added this second liner, which make the blank flat and increase the resistance. Anyway, the first fluting size, so the flutes or the waves have different characteristics. The A is the larger wave. Then we have the B that is smaller. Then they realized that A was too large for some applications, B was too short for some applications, so they invented the C with the size in the between, and more recently E, F, G, and very small waves sizes have been invented. So what we call the micro corrugated. So A is the large, B is the small, but then C is the medium. That's why they apparently do not follow a logic order, but this was how it was invented. So here we see the characteristics, the height of the wave, and here is the number of waves per linear meter. And of course in the micros we have much more than in the large. And the take-up is the amount of material needed for 1 meter of corrugated. So we have different characteristics. This is regarding the sizes, but regarding the performance is also different. Okay? A is excellent for the stacking resistance, but is weak for printing. Okay, we don't see such a good printing when we look into the printed image on a board made out of corrugated type A. Is not so nice, because we can see a little bit the waves. So printing is better when we have micro corrugated, so very small waves. But in this case we have weak stacking performance, and so on. Okay, so during the production of the box or transformation of the board into the box, like we have operations for printing, die cutting, and so on. And we also have requirements for the use of the box. So combining this, is these two, to balance these two types of requirements, need that we often need to combine different types of flutes. And this is why often we don't see, when we have the double or the triple structure, the flutes are not equal. We have smaller in one layer and larger in the other layer. Okay? So if we want a box, to produce a box that needs to be to have high stacking resistance, but at the same time we want to have a nice marketing image, so we need to have a good printing. So we will put a flute, a wave of smaller size on the outside to where the printing is going to be applied, and we use a larger wave on the inner face for the stacking capacity. And regarding the dimensions optimization, I think we can see better in this picture what we ended in the last section, when I explained that the dimensions of the box are always length, width, and depth, being the length the longest side of the opening side, and the width is the shortest, and the depth is the third. So we have these two boxes. They have the same dimensions, but the opening side of this one is this side, while this is this side. So in this case, in this box case, the length is this, the width is this, and the depth is this, while in this box the length is this dimension, the width, and the depth. Okay? So to distinguish, we use always the same order, length, width, and dimension, but we need not to forget that the length is not the longest dimension, is just the longest of the side where the filling of the box is done, and that depends on the filling line. Okay, so this is important when ordering boxes, because if we mess this, then in the line we cannot fill the boxes, and we need to change the setup, which is not good. Any questions? It's clear. Okay, we have the FEFCO code, like in the folding cartons case. In this, for corrugated board, we have the federation. This is FEFCO is from French, so it's the Federation of European Producers of Corrugated Board. And if you look into the boxes, most of them, they have this label where they are stamped according to the quality of the board. We have different grades inside each category: single wall, or but class 2 and double wall here. And so we have in this direction, we have the better, the more resistance boxes. And this is evaluated by 3 type of tests that are very common as specifications, which is the Mullen test. The Mullen test is the resistance to bursting, we will see, and the perforation, and the ECT is the edge crush test. So it's resistance to stacking, is a measure of the resistance to stacking. We will see. So these three parameters are the most important and always used by industry to as a specifications and as a classifications against the FEFCO code. Very important for packaging is how the joint is fixed, glued, or that is what is most common. In the older times, and still for some cases is stitched joint, but now because of safety issues, all metal parts, even in transportation packaging, is avoided, and stitches, metallic stitches are becoming less and less used. So it's either taped or glued. And here are a few examples of the FEF code. We have here the complete set. Again, we use numbers to designate the different types. We have the most simple boxes are the slotted type, and here you have the first, this is the most commonly used box, and this is the second one. Can you figure out the main difference between these two boxes? So you see here the box in the plan flat form, and here you see being set up. Okay? Can you see the major difference between the two? Yes, here is a completely rectangular, and here is not. So what are the two major implications of this difference? This is a difference, yes, you spotted correctly. This is not a perfect rectangular. This is a nearly perfect rectangular. But this has two major implications. Now you must look into here. Yeah. This looks like playing games, but this is real life in packaging industry or in food industry. These boxes they have completely different performances, costs. Okay, in this case, you see that the inner flaps, they don't touch, while here, they do touch. The outer flaps, they always touch, otherwise, the box will be open. There would be a hole there. So the outer flaps always touch each other in the middle. But the inner, the ones that go first, here they do not touch, so we see a hole in here, and here we don't. So this is the first implication. The strength resistance of this box is much bigger because we have the two flaps inside and the two flaps outside touching each other. This is one implication. Which is the second implication? When I'm doing this box, I have scrap of this. Scrap. So these pieces of the pieces of board that would be here are wasted. They are not used. So from the environmental point of view, in the production, this box produces higher amount of waste of board, because I need to cut here. So, because you understand that these are the flaps from outside, and this is the flaps from the inside. So I need a piece of board wider to produce this, because I need these flaps to be bigger to touch each other. So this generates higher waste in the production. Okay? Only if my box would be squared, I would not have this problem. But I would have other complications. Okay? We have other types of boxes, like number 3, we have 2 pieces. Number 4, we have kind of envelopes, and so on. Okay, so if you want to see exactly other codes, other types, you can go into the code, into the FEV code, and you read there. Now here we have, we start with some specifications, measurements. Okay, the first one is the thickness and the grammar. Okay, and we see here very clear different, or see this type of double is the one as example as the one that I mentioned before. We have a layer of a small flute and a layer of a large flute. In this case, we have 2 flutes layers that are the same. So we need to address this to characterize our material. So the thickness, the total, the partial, and the same for the grammar. Okay. The bursting test, as I indicated, or also known in industry as the Mullen test, is to measure the bursting strength of the paper or paperboard. I could not use here photos of the equipment, but we see here that we, as a scheme, we apply a force up to bursting the board, and the pressure required is recorded, and this is performed on each side, each layer, each side of the board layers, and usually is expressed as the average of both. But it depends on how you want to evaluate your material. The edge crush test, or the ECT, we cut a little bit of board and we do a compression test on the direction of the compression of the box. Okay, in a box, a typical box design, there are a few exceptions, but typically the flutes are aligned in this direction, so for higher stacking resistance. Okay, and so this is how the ECT test is measured, and it relates directly to the stacking strength. So this is a test used commonly in the laboratories, but even better to test a small part, a small piece of the board, is to test the box itself. So we have a big table, compression table, and we put the box there, empty or filled, and we compress the BCT. So this is the BCT stands for box compression test. And there is a Mackey relationship that is valid only for one type of box, that the FEFCO 0201, so the more simple box type. This is the Mackey relationship that relates the box compression with the compression obtained by the previous test, the ECT, the thickness or caliper of the corrugated board, and the box perimeter. Of course, a bigger box resists more, so it depends on the perimeter of the box. So because the BCT test requires equipment that is more expensive, not all laboratories are able to have it. So there is this relationship between the ECT and the BCT test. And we have another test, that's the FCT, or flat crush test, where we compress the waves not in the direction as they are in the box, but on the cross section, on the cross direction. So it's a flat crush test. So this is a measure of the resistance of the flutes, and this is important. This is an important characteristic for the production operations, not so much for the use life of the box, but for the production operations, printing and so on. And we have the bending stiffness test. Is important for boards, for paper also, and for corrugated board. It can be applied to the three materials. Is defined as the bending moment per unit of width. So here is to bend, not to fold, because there is a similar test to measure the folding resistance, is to bend. So typically we want a board that has higher bending stiffness. It means that the box will not deform easily during the stacking, during the use of the article, of the box. And finally, the other very important specification is the water absorption of the paper. We want the paper not to absorb moisture. So we do these Cobb tests, that's how it is called, in looking for low values, not for high values. So it's referred to the ability of this material to resist the penetration. And do you have any idea on how this can be achieved in paperboard materials? How do we decrease the normal ability of absorbing moisture? We play, or the producers play, with some operations like beating the fibers, and we play with the composition, with some additives, some resins that are mixed with pulp in order to decrease this water absorption. So the Cobb test is, as it is here, sizing, porosity, and composition are the characteristics of the board that determine the water absorption. And this test is made, performed by simply weighting a piece of paper, putting it in contact with water in a circular ring so that the water will contact the paper only inside that area for a certain type of, for a certain time. And then we weight the paper again, and we realize how much water it has been absorbed. So it's a rather simple test. It has some standards. This must be done in a certain way, but very simply is like this. Okay? So this is the last for this topic, for the corrugated board. So we have seen a little bit on the paper composition, types of papers and types of packages. We have made some information on the labels that are very important for bottles. And then for paperboard and corrugated board, we have seen the structures of the materials and the designs codes according to the industry that for this sector is very important, and a little bit on specifications.